Hello everyone, welcome to the linear elasticity course. In this video we're going to continue the topic that we started the previous meeting regarding the mechanics of particles and its relation to the continuum mechanics, or in other words how the movement of the particles inside the continuum or inside the material would affect its mechanics. And as we discussed in the previous meeting, mechanics, it means that the study of the behavior of material when it is subjected to different excitations or different forces. These forces would be in the form of magnetic force, mechanical force, electrical force. So our main interest is to understand how these materials are going to behave under different applications or different forces. And like the previous meeting, we already discussed the theory of the classical mechanics, and this is the main theory that we're going to consider through this class or this course, that the classical mechanics assume that the material is homogeneous. Also, it assumes that the material is a composition of an infinite number of points, and each one of these points, or an infinite number of particles, and each one of these particles is represented as a point. Also, we discussed that the particle is a representation of the material's main building unit, and we give an example for a polycrystalline material that the grain itself, it will be represented as a particle in the context of the classical mechanics, or in the context of the mechanics. In the classical mechanics, this grain, which is the particle, is going to be represented as a point. And also we discussed that the point, it has only one type of degree of freedom, that it can move along either x, y, or z, but there is no rotation, there is no deformation for that point, since it is just a point, right? Then we consider some, we focused somehow on the mechanics of particles, and we consider two main examples, like the monatomic lattice model and the diatomic lattice model. Then we moved, and through these two examples, basically we focused on the movement of the particle and the types and the modes of vibration of the particles or these atoms with respect to each other. Then we moved to the general concept of the mechanics of particles, and we drive the general model that of a discrete system of particles, and we end up these with these two equations that describe the dynamic equilibrium of a particle particle n that is located within a discrete system of particles. And this is the last thing that we ended up with the previous meeting. So starting from this part that we finished with the previous meeting, we're gonna continue here, and the focus of today's lecture is on the continuum mechanics. So first I'm going to show you how we can smoothly move from the mechanics of particles to the continuum mechanics, how we can drive the equilibrium equations that we're going to use in the continuum mechanics. And starting from the equilibrium equations, or the equation of motion that we got, which is the equation 11 that we got the previous meeting for the mechanics of particles. So just very quick, I'm going to go over this equation one more time to to reset some points here. As we mentioned, that this Fn, this is the interatomic potential, or the interaction between two particles. One particle, which is our main interest here, is the particle n, and the other particle is particle m, where this particle m is a neighbor to the particle n. And we are interested in this equation describe the dynamic equilibrium of the particle n under the influence of the forces, where this force, again, this is the force of interaction between two particles like particle n and m. But in addition to this, and in order to to consider the dynamic equilibrium of the particle, we have to collect all the forces that generate between the particle or any other particle surrounding the main particle n. Like this m stands for the neighbor particles, and nm stands for the number of these neighbor particles. And our main interest is just to calculate the force. Like you already have a particle n, and there are lots of other particles surrounding it. So between this particle n and these other particles, there should be different interactions. So we're gonna sum all of these interactions. This is like F1, and this is like F2 and F3 and so on. Summing all of these forces, this gives this summation term equal the mass times the acceleration u double dot. As you know, this is the acceleration of the particle itself, and this is according to the Newtonian's law. But also we discussed that the force, it has another effect, that it would have produce a moment, and this moment it would result in some rigid body rotation of the whole discrete system. Like if we are interested in the dynamic equilibrium of just the particle and we don't care about what's going on with the overall, the entire system, this discrete system, we have no interest into the second equation. But this second equation should be used if we are interested to know what's going on in the overall system of particles. So in this case, we have to consider the second equation, or consider the moment due to that force, as we discussed in the previous meeting, as x, the cross product of x, which is just a displacement, or the displacement vector. This is just a vector, and the force is another vector. The cross product gives a vector which related to the rotor inertia of this discrete system of particles. Like you're gonna assume that all of these particles are going to rotate rigidly because of these forces that generate between them. Also, we said that in addition to this force, we may have some external forces here, like F external, which would affecting on directly over the particle. Also, we may have an external moment, or you consider that, or we can say that this external moment is a direct effect due to the force, the external force, or it would be directly as independent moment. Like we can say that this particle is subjected, or this discrete system of particle, here I'm talking about the overall system, that is subjected to some moments that gives it rotation, or this particle, but this if external, this is the external force that acting on the particle itself, just directly over particle n. Okay, and as we discussed in the previous meeting, this particle n cannot support a moment. It means that why? Because this is just a point. According to the classical mechanics, a point it cannot rotate. So it cannot support a moment, but the overall system itself, it can support a moment m, like m external, and in this case, the overall system, discrete system of particles is going to rotate. This is another thing. So you should consider that this equation kind of is a separate equation. It is independent equation than this one. Like for example, in many cases, that is fine to neglect or just to assume that, or give no care to the second equation. This equation here, we are talking about the system, the overall system itself. But here we're just talking about the particle, the equilibrium of the particle. So if our interest is just the equilibrium of the particle, we need just the first equation. But if we are interested in the equilibrium of the overall system, we have to consider as well the second equation. Make sense? So this is basically what we end up with the previous meeting. So we're gonna start from here, but now we're gonna move to the continuum mechanics. This is for the mechanics of particles. So now let us make it more general. How about if these particles, or this discrete system of particle, it is huge, or the number of particles is huge, in some way to form a continuum. So let us consider this case. Assume that we do have a continuum, and this continuum definitely is going to be composed of so many particles. Like we do have so many particles already interacting together inside this continuum material. So there are lots of interaction forces between all of these particles inside the continuum and so on, right? So all of these are different interaction forces. And let us assume that the number of particles is huge, is infinity, tends to infinity, very huge number of particles. It is hard for us to count how many particles do have. And now let us consider that this continuum, there are some special particles that are located over a surface of this continuum in this way. Like there are lots of particles, and even the number of particles over the surface, it is huge. It is uncounted one because it is so many, right? So these particles, in fact, that are located over the surface should be different somehow than the particles inside the continuum itself. Assume that this is a continuum. Continuum, it means that just a material, solid material, for example. This is a continuum, and there are lots of particles located over the surface, lots of particles inside the continuum, or this is the continuum core. But if you remember from the physics or even the fluid mechanics, some courses, like the interactions between the particles over the surface is different than the interactions between the particles inside the core. Or in other words, we could say that the interaction force generated over the particles over the surface will be definitely different than the interaction forces between the particles inside the core. Why? If we consider one particle inside, this is core particle, this is the core particle. So this particle will be surrounded with some other core particles everywhere, right? So there should be some interaction force here between this particle and the one to the left, one to the right, one on the top, one on blue, right? So it means that this particle, which is the particle inside the continuum, it will be with an interaction or with interaction with all the particles surrounding it, and this interaction forces are everywhere, like it is already have interaction from all directions. But if we consider the particle that is located over the surface, so over the surface, it means that there should be some particles below it, but there is no particles on above the particle. This is our main particle surface. This is the surface here. This is the surface particle. So the interaction here, this particle will have some interaction to the one on the right, some interaction to the one on the left, some interaction to this particle, some interaction to this one. But there is no interactions on the above or the top side. Above this particle, there is no other particles to have interactions with. So what does it mean? It means that there should be definitely this particle, it should be in equilibrium like this one. So the interaction forces here will be definitely different. This is what generates the surface tension effect, for example, or generally in terms of solid mechanics, this what generates the surface stresses over the particles located over the surface. Right? So I just explained this thing, I brought this thing here just to let you know that the particles over the surface will exhibit some deformation or some stresses or some fields which are different than the particle inside. And the main reason comes because of these, the difference or the distinction between the interactions of the particle that is located over the surface and the particle that is located inside the core. Make sense? But generally, we do have a continuum that is that already having like lots of particles, so many particles in the core and lots of other particles, so many particles that distributed over the surface. And that's why we do have a surface for any material that in many cases the surface will have properties that different than the core of the material itself. But anyway, skip this point for now and let us consider going back to this continuum. And let us assume that we are going to subject this continuum to some external forces like force F external, for example, or some external moment, or whatever. It means that in general we're gonna have, forget about the moment for now, let us focus on the force. Assume that we have some external forces that already acting over this continuum. So these forces should do something to this continuum material. And we knew this from the mechanics of material class or even from the dynamics class. One of the options, for example, if let us assume that we're gonna put some wheels here, some rollers to this material over the surface, and we try to push this material, so this material, it will be definitely moved. So this is one of the results of the external force that acts over this continuum. And remember that this continuum consists of infinite number of particles, right? The other option, if we put some constraints over this particle to prevent it motion or to prevent it to be moving, so in this case we're going to end up with some deformation, and this is what we knew from the mechanics of material class. So we do have in general, because of the external force, we have two options. The first option that this continuum is going to move, the second option that it's going to deform. The third option is going to do combination between deformation and motion. It means that it can move and deform in the meanwhile. Make sense? So this is general. It means that this external force should do something to this continuum material, to this material. Make sense? So now, forget about this point for now, and let us go back here to this equation. So these two equations describe the equilibrium of one particle or a discrete system of particles in this way, right? This is here we are talking about the particle. Now, how about the equilibrium equations or the equation of motion but for the continuum? And this continuum is consisted of an infinite number of particles. So can we derive the equation of this continuum from the equations of the discrete system of particles? Yes. For example, what is the difference between this discrete system of particle and this continuous system of particle? Continuum, it means that there is continuity, there is infinite number of particles. So there is continuity in the field everywhere inside the material. This is the meaning of a continuum, right? But the difference between the discrete system of particle and the infinite number of particles, that here we can count the number of particles. It is discrete. So what does it mean? It is countable. It means that we can count how many particles we can collect, we can sum. So that's why we have the summation here that indicate we are calculating the force between this particle and the next particle, the force between this particle and the next particle, and so on. So as we collecting, as we end up with some fields, with some interactions, with some forces, we can collect these forces as long as this system is a discrete system that we can count how many particles. But in case that we do have infinite number of particles, huge number of particles, here we cannot count how many particles and we cannot collect. And for this case, that is fine to replace the summation into integration over the volume of this continuum, because these particles, their number is huge, but we are pretty sure how much they are because they form a continuum with a specific volume, because we do have an idea about the volume of this continuum material or this material. So instead of counting, it will be hard for us. That is fine to integrate. And if you remember, even from the mathematics, one of the application of the integration, that you already sum some things over each other. Like you do have integration of a field, integration of a function. It means that you're gonna calculate the function at different points, then you sum all of these functions or all of these values of the function at these discrete points at different points to end up with the integration. So the integration, it can be approximated like the summation of functions over different points. So here we're already summing because we can count, but here we cannot count how much, so we have to replace the summation with integration. If we did so, we can derive the equations of the continuum, but from the equations of the mechanics of particle or the discrete system of particle, and this is what we're gonna do. So to derive these equations, let us again consider the continuum. Like assume that we do have this continuum body again, and as we mentioned that this continuum consists of so many particles, infinite number of particles, so we cannot locate or identify a specific particle inside this continuum. So we have no ability except that we can assume that each one of these particles is just a point according to the classical mechanics, and this point it can only move with a displacement field u of x. What is u of x? This is the displacement of one particle that is located at point x. So this is x, this is the location, and this x should be a vector if we're gonna talk about the three-dimensional space like x, y, and z directions in this 3-dimension. So assume that you have a point in the classical mechanics. This is a particle for this material, right? That is located at a point x. This particle is going to move with a displacement u of x due to some external forces. This is the concept of mechanics. Mechanics is to estimate or to calculate how much is u of x, how much is the displacement of any point that belong to a material, that belong to a continuum due to some external forces. This is simply what does it mean mechanics, okay? So, and based on our discussion that this point is just a particle, so, and this particle is going to move with a displacement u of x. So, for this particle to exhibit this displacement, to move, there should be some external forces, as I mentioned. There should be some forces. Otherwise, if there is no forces acting on this particle will do nothing. This particle will not move, right? So, to understand these forces that would act on a particle, let us consider this particle on the side here. Like this is the particle itself, whatever it is, it's just a point. And these forces that would act over this particle, it would be forces between the particle and the other surrounding particle, as we explained in the discrete system above here, right? We said that, oh, anyway, there should be some interaction between this particle and the surrounding particles. So one of the forces, actually, it should be some interaction forces between this particle, which we give it a name when we consider the discrete system of particle like F in M. So there should be F in M, that it should be a vector. This is a force vector. This is one of the forces that would act or affect on the particle. Make sense? Like this force is coming because of the interaction between the particle and the surrounding particle. So there should be some interactions here, right? Assume that all of these interactions, their sum together is just F in M, or just F. Is just a force of interaction, and this is the interaction of the particle that is located at X. Here we cannot number, we cannot give a name to the particle N as we did here. Particle N, we cannot locate this particle or identify this particle inside the continuum. But here we're gonna identify or distinguish between the particle as a point. So that's why this is the particle that is located at point X. It will be subjected to some interaction between the particle and the other particles within the continuum. But in addition to this force, there should be some other forces that would act. There would be some external force, F external. This external force comes directly, acting directly onto the particle itself inside the material. This force is already internal force. It means that it is external force that comes from any external excitation acting directly on the particle. But in addition to this external force that act on the particle, there should be some external force that act on the surface of the continuum. That this external force, and we're gonna give it a name like T vector. This is like T vector. This T vector is a surface traction. Surface traction, what does it mean? It means that this is a force that acts only over the surface of the continuum. It is not directly acting on the particle inside. Make sense? In addition to these forces, so one of the forces, which is the conventional one that we discussed due to the interaction, also there would be some external force, but this external force, it would be special somehow to be directly acting on the particle. An example of this external force is that you subject this overall continuum into pressure. So this pressure will be transferred somehow to be a direct force acting directly over the particle. Make sense? But in addition to this direct force that would act on the particle directly, we may have some external force that comes over the surface. So this external force T will definitely have an effect over the particle, but this effect is indirect one. Why? Because this surface, this force T, it does not affect over the particle, it affects over the surface of the continuum to which the particle belong. It means that this particle belongs to this continuum, so any force acting over the continuum will be definitely affect the motion of this particle. Make sense? But the effect of the motion or the effect of this force T is indirect effect. This force T is known as surface traction. We're gonna give it a name as surface traction. Traction like force. Traction, it means force. It is known as a surface force or a surface traction acting on the surface of the continuum. Make sense? In addition to these forces, so far we discussed like 3 different types of forces. In addition to these forces, we may have one force that depend on the weight of the particle. We may have a force like mg. This is the mass of the particle times g, which is the gravitational acceleration. This is the weight of the particle itself, which is commonly known as the gravitational force. This is the gravitational force acting on the particle. Make sense? So the forces that would act on a specific particle are so many. It would be interaction, as I mentioned, between the particle and the surrounding particle. It would be external force that directly acting on the particle. It would be the weight of the particle itself. It is one of the forces because the weight is a force, right? Or it would be some indirect effects due to surface interaction acting on the continuum itself. Make sense? In addition to these forces, there would be some other forces that would be generating because of a magnetic field, because of electrical field. For example, how about if we do have this particle has a positive charge and the other particles do have a negative charge. So we're gonna have another force that is gonna be generating due to the polarity of the difference in the polarity between the particle and the surrounding particle. So we're gonna have another force as if electrical, for example, that comes because that depend on the polarity difference between these particles. So anyway, all of these are different forms of forces that would act on the particle. Some of these forces are indirect and some of these forces are direct forces. Make sense? So in terms of continuum mechanics, to distinguish between, or we're gonna discuss these different types of forces, or we're gonna consider them again. But now we would like to form the equilibrium equations or the equation of motion of the continuum itself. So we have to derive this equation, as I mentioned, from these equations. By doing integration, we cannot sum again the particle, but we have no ability except that we integrate. But here in this equation, we're already summing all the forces. On the left hand side, what we are doing, we're already collecting all the forces acting on the particle. That the equations of motion are two main equations, right? In the first equation here, on the left hand side, we're already collecting all the forces acting on the particle. These forces would be external force, would be the interaction between the particles, it would be a force due to the weight of the particle, due to electric field or magnetic field acting on the particle. Just sum all the forces that would act on the particle here. So what we're gonna do, if I ask you just to write the equilibrium equation for just one particle, under the influence of all of these forces, the direct forces here. So we're gonna write this equation like, we're gonna say that for just this particle, we do have F electric, right? Which comes from electric field, plus a force of Nm, which is the force that comes due to the interaction between the particle and the surrounding particle. There would be some external force, F external. There should be weight, right? Which is just mt. This is the weight of the particle, the weight W of the particle itself, or any other force that directly acting on the particle, according to the first equation, right? Sum all and collect all of these forces. But you should understand something here, that this is the weight of the particle that is located at point X. This is the external force that acting on the particle that is located at point X. This is the interaction force that is acting on the particle that is located at point X, and so on. As you keep moving, all of these are just identified for just one particle. But for this continuum, it has so many particles. It is not just one particle. So what does it mean to calculate or sum or collect all the forces that act over all the particles? We have to do integration here. So we're gonna do integration over the volume of all of these force fields, or all of these forces that act on just one particle that is located at X. We're gonna sum over the volume. Why we are sum over the volume? Why we are integrating? Because we cannot sum these forces. We cannot count the particles. So we have to do the integration. Make sense? So this is the forces. These are all the forces that act over just one particle inside here. Make sense? But remember that our main interest is to find the equilibrium equations or the equations of motion of the continuum. In addition to these forces that directly act over the particle, there would be some external forces that act over the surface of the continuum, as I mentioned, right? And if we zoom to the surface, we said that the surface, it has also particles, right? The surface, it has some special particle that located over the surface. So you could say that this sum here, this integration collects all the forces that act over the core particle, the particle that located inside the core of the continuum. But how about the other particle that already located over the surface? They are different. They're gonna subject to different forces. They're gonna subject to different fields. As we explained here, the interaction between the particles in the core is different than the interaction between the particles over the surface. Make sense? So if we consider that these particles over, so now let us just pick one particle that belongs to the surface. One particle on the side here, just collect one particle that belong to the surface. Okay, let me just pick this one here. Like assume that these surface particles, and let us pick one particle, I don't know, okay. Let us draw this particle here. So this is just a surface particle, and this surface particle, as I mentioned, it has some interactions with the particles underneath the particle itself, but there is no interactions on the top of the particle. It means that the Fnm for this particle will be definitely different than the Fnm, which is the interaction force of this particle that is inside the core. This particle, the interaction forces between the particle and the other particle will be definitely different than this Fn. So I'm gonna give it like Fnm surface, because this is just for the particles located over the surface. This interaction field or force, it will be different than this interaction force. Make sense? In addition to this force, we may have here some external force that act over this particle, and we said that we're gonna give it a name like T. T, this is the surface traction that already acting over the surface. So this force will be definitely acting over the particle that is located over the surface of this continuum. Make sense? In addition to this T, in addition to this Fnm, there would be some electric force. So we're gonna have like F electric, but it would be different. Some electric force, surface, that this electric force that acting on the particle over the surface will be definitely different than the electric force acting on the particle inside the continuum core. In addition, this particle may have a weight that would be different than the weight of the other particle, or it would be the same. It depends, right? So let us assume that this is like the weight force for the particle that is located over the surface, and so on. Make sense? In addition, for example, in case that you do have, we discussed the external force, which is just T. So all of these are different forces acting over the particle that is located over the surface. So it means that if I ask you to collect all of the forces over one particle over the surface, all of these forces will be definitely equal. If you just sum all of these forces plus these forces, this is gonna give us the Fnm surface plus the T, which is the external force, plus the F electric, which surface, plus the weight surface. Make sense? All of these forces are located or acting on a particle that is located over the surface at point X that belong to the continuum. This is also at point X, this is at point X, this is at point X. But remember that all of these forces acting over the surface. To collect them, we have to integrate, but integrate over the surface. Here we cannot integrate over the volume. Why we don't do integration over the volume? Because these particles are located over the surface. So to collect all of these particles, you have to do integration over the surface, not over the volume. And the surface integral, it is like you already summing over an area. Surface, it is like area, it is not a volume. So that's why we're gonna end up here with two different integrations. One is integration over the volume, that to collect all the forces acting on a particle inside the continuum, in addition to surface integral that collect all the forces that would act on a particle located over the surface of the continuum. Make sense? All of these forces, we summed all of them together. So now we end up with the right hand side of the first equation. This is just the right hand side of this first equation, that we sum all the forces acting over all the particle of the continuum. But these particles are like two different domains, two different things. Some particles inside the core and some particles over the surface. The forces over the particle inside the core are different than the forces acting on the particle on the surface. So that's why we're gonna collect all the forces acting on the core particles, and then we're gonna collect all the forces acting on the core, the surface particles. Then once we collect all of these forces, we're gonna integrate, do integration to sum all of them within the domain, whatever integration over the volume or over the surface. Make sense? All of this integration, it should equal to the inertia. So if we're gonna go back here, now we're gonna move to the left hand side, the right hand side. The right hand side, it is we are integrating here, so we have to do integration to this term as well. So this is gonna give us here equals the integration over the volume of the mass of the particle times the displacement double dot, which is the acceleration of the particle that is located at point x dv, where dv, this is the integration of the over the volume. So this is going to give us the first equation, but for a continuum. This is the first equation for a continuum. This one is the first equation for a discrete system of particles. Make sense? How about the second equation? If you just compare the first equation to the second, or the second equation to the first equation, you're going to see that we're already calculating the moment due to the forces. On the left hand side, there should be some forces. Here we are getting the moment of these forces. Here we are giving the moment, the inertia moment. This is the inertia force, this is the inertia moment. So simply we're gonna multiply all of these force terms times the cross x, or the cross multiplication with x. So the second equation definitely will be, if I decided to write the second equation, will be as well integration over the volume, because we're already collecting over the volume. Your objective, all of these just forces. So the moment from any one of these forces should be x cross this force. So I can simply write this one as x cross multiplication of all of these forces, all of them together, as F electric plus the of particle that is located at x of F n m plus the weight plus the external force dv. Make sense? This is the moment from this term, plus also there are some forces over the surface. They do have a moment. The moment it is simply the multiplication of this, the cross product of this one with the x, which is the position vector. So this is going to give us the integration over the surface of x cross the multiplication of these surface forces, which are the Fnms plus the weight of the particle located over the surface plus the force of interaction of the particle located over the surface plus the external force, which we just agreed to give it a name like T, ds. Here we're gonna do integration over the surface. Make sense? Then what we're gonna do, this should equal to the, now if we did this, so this is gonna give us here this term. We're just gonna carry on this term, which should be the equal the integration of the volume of mu double dot of x dv. So this is gonna give us the second equation. So this is the first equation, this is like equation 1, and this is the second equation of equilibrium or dynamic equilibrium of the continuum, that is equivalent to the equations of motion of a discrete system of particles that we draft up there. Make sense? Now let us do a little bit simplification here to this equation, because we had considered lots of force terms. How about if I decided to combine all of these force terms into just one force field as f of x? This is the total force, all the forces acting over the particle that is located inside the core of the continuum. Make sense? And then I'm gonna do the same. I'm gonna collect all of these forces that act over the particle that is located over the surface of the continuum, and I'm gonna give it a name like T of S, where T, this is the surface traction, that it would be the similar like this one, but this is a more general one that collect all of the forces acting on over the particle located over the surface. So instead of using multiple terms of the forces, it is convenient to combine all of these forces into just one force component. But this force component, you should understand, it had been generated from so many forces acting on the particle that is located in the core, or so many forces acting on the particle that is located over the surface of the continuum. Make sense? And we're gonna give a name to this force as a body force. This is in terms of elasticity, is known as a body force. If you open any textbook of continuum mechanics or elasticity and read, they're gonna represent the equilibrium equation of the continuum, and they're gonna mention that we do have F, and F is a body force. So what is a body force? A body force, as I just explained, it's any force acting on the particle located inside the core of the particle. This force, it would be interaction forces, it would be electric field, it would be magnetic force, it would be external force, it would be the weight of the particle. All of these are different forms of body forces. But in addition to these forces, there are some other forces that act over the particle located over the surface of the continuum. We have to collect all the forces over all the continuum. So we do have particles in the core, and we do have some other particles over the surface. So we have to collect the forces acting on the particle over the surface too. These forces, we can sum all of them together, that it would be interaction force, external force, electric force, magnetic force, weight, whatever they are. Collect all of them together into one term and give it an name T, which is the external surface traction or the external force. This F is commonly known as body force, this T is commonly known as the surface traction. Where the surface traction, it would be any form. It would be, as I mentioned, external force, weight, whatever it is. And this is the inertia force, which is mu. It should be accurately, exactly, it should be mu here. Mu, this is the inertia force. I forgot something here, that this inertia force, it should be multiplied times x in this term. Let me remove this part. This term, it should be the x cross product of the mu double dot of x. Make sense? Where this term will be the inertia moment. So going back here, so these are, that is fine, as we agreed, we're gonna combine all of these forces together, whatever they are, into one component of forces known as the body force, in addition to the forces located over the surface and the surface tractions. We're gonna do the same here. So we can combine all of these forces into just F of x, and we're gonna combine all of these forces into just T of x, which is the surface traction. So we're gonna end up with a more compact form of these equations as follows. The first equation becomes the integration over the volume of the overall body forces over the volume plus the integration over the surface of the surface tractions ds equal the integration over the volume of the mass of the particle times the u double dot of x dv. This is gonna give us the first equilibrium equation of the continuum, and the second equilibrium equation of the continuum, it will be definitely the integration of x cross f of x, where f of x, again, this is the total body force that would exist or generate due to any forces acting on the particle located inside the continuum, times plus the integration of the surface of the x cross the T of S, where T of S is just surface traction that act over the force, the particle located over the surface, times the equal the integration of over the volume of x cross the mu double dot of x dv. This is gonna give us the second equation. So these are the two equations of equilibrium for a continuum, and these two equations are the equations of a discrete system of particles. Here we can count the number of particles, but here we do have a continuum with infinite number of particles, so we had to do the integrations. Make sense? So these are the two equations, and now let us demonstrate some, just to conclude some points here. So if we assume the volume V, a continuum with a volume V and bounded by surface S, where S stands for the surface of the continuum, and this particle consists of a huge number, 10 to the infinity of particles. Each one of these particles, we cannot locate a particle anymore, and in this case we have to consider that the particle that is located at X, we cannot give a name, or we cannot say that particle N, we don't see N, but we're gonna say that the particle that is located at point X according to the continuum limit that we're already dealing with. So we're gonna end up with these two equations. These are the two equations that we got by integration of equation 11 that we did for above. These are the two equations for the continuum. So these are the equilibrium equation for the continuum, as we draw them from the mechanics of particle. Again, if it is the body force, and we said that this body force vector, it is a force vector. This F, it is a force vector, like T, it is a vector, U is a vector, X, F, everything in these two equations are vectors, right? So this body force vector represents all forces acting on the particle located inside the continuum core at a point X. Body forces would include external body forces, interactions between particles, or gravitational force like the weight, as I mentioned. Also, in addition to this body force, we do have here in this equation T. T is an external surface force vector also. It is commonly known as surface traction vector or surface traction. This vector represents all forces that act on the particle located on the surface of the continuum. Last thing that I'd like to mention here, that these two equations of the continuum equilibrium, we can solve them somehow to find u of x. What is u of x? This is the displacement field. Again, what is a field? As we discussed before in the vector and tensor calculus, this is a function that describes a specific phenomenon. Here we are talking about a continuum, and this continuum would exhibit some changes in shape, or it would move because of some external forces, right? So how we can describe one of the things, for example, to describe how much this continuum will be affected because of the external force, is to calculate the displacement of its particles, how these particles are moving inside the continuum, as we discussed before, right? So it means that to solve these equations, solving these two equations is just to find the displacement of any point that is located inside the continuum. And remember that this point is a particle, refers to a particle. It means that if we can, or in other, as I just mentioned, solve these two equations, we're going to end up with u, which is the displacement field of the particle or the continuum that describe the motion of the particle. And because of this motion of the particle, as we discussed above, this continuum, it would move or it would deform. So generally, because of the movement here, the movement of the particle would produce some deformation in the continuum. Deformation, and this is one of the keywords that we're gonna use a lot through this course, and we're gonna, even in today's lecture, we're gonna discuss what does it mean deformation with more details. But deformation generally is any change in the shape, the dimensions, or the position of the continuum. Because of what? Because of the external force. As I mentioned above, you do have a continuum, you do have a solid material, and you're gonna subject this material into some external forces. This force should do something to this material. This something will be definitely seen as deformation. This deformation, it would be change in the shape of the continuum. Like, because of the external force, the material shape is going to change. And you should understand that the change in the shape or the dimensions of the material will be temporary. It will not be permanent. If it is permanent, it means that we had moved to the plastic deformation. But in this course, we are working as elastic. So elastic, it means that once the effect of the external force will be removed, the material will restore its original shape and dimension back again. But in terms of elasticity, that because of the external force, the material is going to do changes or exhibit some changes in the shape or the dimensions of the material because of the external force. This is one option or one thing. Another option that this material would move. Move, it means that it's going to change its position. So change in the position, change in the shape or dimension, this is described or commonly known as deformation in terms of continuum mechanics or in terms of the classical mechanics in general. So in mechanics, deformation means a change in shape, dimensions or position of the continuum. As we agreed that we had, so what we did so far, basically we have derived some equations of the discrete system of particle, and from this equation we end up with these two equations 12 and 13 for the continuum that is consisting of an infinite number of particles. And as I mentioned, the objective is to solve these two equations to end up with the displacement field. But as you can see, we do have here body forces, which are the F, in addition to surface tractions, in addition to some inertia forces, right? Also, another thing that we can observe here, that we do have different types of integrations here. This is a volume integration. This is integration over the volume. This is surface integral, which is integration over the surface of the continuum. And the same thing here, we do have a surface integral. So to have this hybrid thing in the integral types in one differential equation or in one equation, because this is ordinary or partial differential equation, in one equation it will be hard for us mathematically to solve this equation. It is much more convenient to convert either the volume integral into a surface integral or the surface integral into a volume integral. It means that mathematically speaking, it is easy for us to solve one equation that include only one type of integration, not just both of them, like surface and volume. So it means that it is much more convenient if we could able to convert this surface integral into a volume integral. This requires the divergence theorem. Make sense? So now, these are the equations of the continuum, but there are another form that it is more convenient to be used, or it is more proper, more easily to use, more practical than this form. But this other form require applying something that we call as the divergence theorem. We have discussed the divergence before in the vector calculus and the tensor calculus, that the divergence, it is simply the gradient dot product of a vector or a tensor, right? This is the divergence. If I ask you the divergence of this vector v or the divergence of a tensor, so simply it's gonna be the nabla dot v. This is the divergence as we discussed in the vector or tensor analysis. So here we're gonna apply something very close, very similar, which is known as the divergence theorem, to convert. The objective here is to convert this surface integral into a volume integral to make it more convenient, more practical form of the equations of motion of the continuum. So what about the divergence theorem? As we discussed here, we do have two hybrid integrals in the equilibrium equation. The divergence theorem states that the surface integral of a field, this field, it would be tensor field, it would be vector field. As we mentioned, that the field, it is anything that is a function describe a specific phenomenon. Like for example here, this force is a force field, it is a function. T, it is a force field, but there is surface traction force field. This is displacement field, which is U, it is a function. So all of these are different forms of fields. So if you have a field and there is surface integral of this field, like in our case, we do have the surface integral of T ds, right? So this is the surface integral of this field, and we do have a surface integral of this field over a closed surface, which is the closed surface of the volume, is equal to the volume integral of the divergence of the same field but over the region inside the surface, which is over the volume, I mean. So mathematically speaking, this is the conventional form of the divergence theorem. That the divergence theorem states that in case that you do have a field, this field is V. This V, it would be vector, it would be tensor, it would be anything, right? Vector or a tensor with any order. So in case that we do have a field like V, And what is n? N is known as the unit normal to the surface. What is a unit normal? If you remember from mathematics that any surface or any plane, consider that you have a plane like XY plane or any surface. So plane, basically we are talking about a flat surface, kind of, to make it easy. If I ask you, mathematically speaking, we can define any plane. It is defined by its normal, unit normal. This is the n vector, which is the vector that is normal to the surface itself, and this vector has a value of unity of 1. So we're gonna say that this is the normal. For example, to give a name, to recall this surface, any surface is distinguished from any other surface by its normal, right? By its unit normal, to be more accurate. So this is the unit normal of this vector, right? So for example, if I say, for example, if I said nx, it means that I'm talking about a surface here. This is surface whose normal is x-axis. For example, if I said ny, this is surface whose normal is y-axis. If I said nz, here I'm talking about a surface whose normal is z-axis, and so on. So generally, the unit vector, it has only 3 components. It has only 3 components. In vector, it has only 3 components because it is just a vector, right? So it is unit normal vector. It has nx, ny, and z. For example, let us, to explain this point, let us assume this cube. Assume that you have this cube shape. Okay. Assume that you have this cube. And let us set up here some coordinates, like this is x-axis, this is y-axis, this is z-axis, right? So if I said that, what should be nx? Nx, once you just mention nx, it means that you are talking about the surface whose normal is x-axis. Which one of all of these 3 surfaces? We can clearly see just 3 surfaces, right? Forget about the other hidden 3 surfaces. This surface, its perpendicular axis or its normal axis is x-axis. So we're gonna say that once we talk or mention nx, so it means that we are talking about this surface. This is nx surface. How about this surface? This surface definitely it will be another surface. This surface it would be this one. It will be ny surface. This is ny surface. Why this one is ny? Because its normal is y-axis. The same thing, this surface it will be the nz surface. Make sense? So this is simply, what does it mean, a unit normal? So according to the divergence theorem, in case that would have the integral of the unit normal to a surface dot product times v. What is v? It is a vector field or a tensor field that acting over this surface, over this plane. Like assume that we do have something here, a vector field that acting over the surface. This vector field or tensor field or whatever it is that acting over the surface, if we decided to do integration of this field over this surface S, this is the surface S, this one has also surface, this one has its own surface area, this it has its own surface area or surface, right? If this integration, it can be converted, this is surface integration, can be converted into integral equation, volume integral, which is equivalent, but we're gonna use the divergence of the same field. So that's why it takes the name as divergence theorem, which has been developed by Gauss. So that's why it is also known as the Gauss theorem. This theorem, simply, it is used and it is commonly used in so many applications. One of the things that we're gonna use here, we're gonna use this one to convert the surface integral into an equivalent volume integral, right? So we're gonna use this theorem to convert this surface integral term into a volume integral term, the same thing we're gonna do for this other term, right? But if we're gonna look here, that this surface integral, it should have a unit dot product of a unit vector, right? And if we're gonna look to this term, assume that this V is a tensor. Let us assume that this V is a tensor. Just work over n dot V, n dot V. So n, it will be ni delta I, where delta I it will be delta x, delta y, delta z, and nx, ny, nz, right? This is just a vector. Dot product of another tensor. This is V is a tensor. Deal with this one like tensor. This is tensor. For now. Dot product of a tensor, this is gonna give us like vi, I'm sorry, we already used the I, so we're gonna use jk delta j delta k. So this is gonna end up with ni vjk, right? And delta I dot delta j, this gives delta ij, right? Delta k. Delta ij, it means that I can replace this one with ni, so we're gonna end up with ni vik delta k. So what does it mean? It means that this dot product here of the unit vector dot tensor gives a vector, right? So it means that according to the divergence theorem, there should be n dot something, right? N dot tensor to end up with a vector here. Then this tensor, it will be converted into the divergence of the tensor according to the divergence theorem. So going back here to this equation here, forget about this one for now, just focus on this equation. This term is the integral, the surface integral of a vector t, ds. There is no n here to apply the divergence theorem, right? We should have n dot something to apply the divergence, to convert this one into a volume. So for this, let us assume that this t, which is just a vector, let us assume t, it is n dot t lowercase, where t lowercase is a second order tensor. Because as we mentioned, n dot tensor, second order tensor gives a vector, right? And this t here, it should be a vector. So I should use a tensor here. Make sense? Because to apply the divergence theorem, I need n dot something, right? In the equation of the continuum that we derived so far, there is no n dot something, there is just t. So simply replace t with n dot something. This something, it should be a second order tensor to give the t as a vector as we just demonstrated, right? So what I'm gonna do, I'm just gonna substitute with this term into the previous two equations here. So we're gonna end up with these two equations in this form. I just replaced, this term was t. This term was t. So I replaced these two terms with n dot t as we demonstrated here. Make sense? All right. So we're gonna end up with these two equations. According to the divergence theorem, this term, which is the integration over the surface of n dot t, t again, it is a second order tensor, and I'm gonna let you know what is this second order tensor. ds equals, this is according to the divergence theorem, it should equal to the integration over the volume of the divergence of the same tensor t dv. This is the equivalent integral form to this surface integral form. Do the same here. For this one, for this term, the integral, the surface integral of x cross product of n dot t ds, this actually should be split into two terms because you're going to do like the integration of the multiplication of two functions, right? So it requires lots of demonstrations here. I won't gonna give it to you, and I won't gonna ask you to do the demonstration of what I'm gonna write right now, but your objective is just to remember this form. Like this integral over the volume over the surface, it will be converted into an equivalent, or basically this term, because we have to do the integration over the surface of the multiplication of multiple functions, or two main functions, the x cross product the n dot t. So this is gonna give us at the end the integration over the volume of x cross the nabla dot t, which is the divergence of the second order tensor t dv, negative the integration over the volume of epsilon, and epsilon, this is a tensor, and I'm gonna need to know what is this tensor, double dot t, which is the second order tensor that we just assumed dv. So again, the first one will be converted according to the divergence theorem very simply, right? Very simple. But the second one, it will be split into two terms. Why? Because as I mentioned, this is integration by parts. But I won't gonna do it for you, and I won't gonna ask you to do it because it has lots of things, and we would like to skip this point or this for now. So it means that it's gonna be split into over these two parts or these two terms. The first one will be x cross product dot nabla dot t. This just to get the divergence of t dv negative the another integration over the volume of negative epsilon double dot t, right? So again, what is this epsilon? This epsilon is the permutation. This is the permutation tensor. What is the permutation tensor? This is the epsilon. This epsilon is just the tensor equals the epsilon ijk, which is the permutation parameter that we considered before, but this is the tensorial form of this parameter. So that's why it has delta I, delta j, delta k. This is triadic. This is third order tensor. Make sense? This is the epsilon, which is the permutation tensor here. And it will be multiplied dot product times t, which is a second order tensor. So you should understand that this is epsilon is a third order tensor. This is third order tensor, but this one is a second order tensor. Make sense? So if you did dot product of a third order tensor times dot a double dot product times the second order tensor, this is gonna give us a vector. So this multiplication gives a vector. This multiplication as well gives a vector because nabla dot tensor gives a vector and vector cross vector gives a vector. So this gives a vector. This term also gives us a vector. So it means that we do have consistency, right? It is just vector. All of these quantities are vector. As well, this one is a vector. This one is a vector, and so on. So your objective is just to consider, substitute these two relations that we demonstrated here, or we wrote here directly into these two equations, right? So the first term, the first equation will be stay still, like integration over the volume of the body force dv. This is just the first term. This integral, it has been converted into this volume integral. So it became the integration over the volume nabla t dv, make sense, equals the right hand side is just the integration over the volume of mu double dot dv. How about the second equation? The first term will be still the same. So the integral of x cross f dv plus this second term has been split into two terms, which the first one at the integration of x cross the nabla dot t dv negative the integration over the volume of epsilon, which is the permutation tensor double dot t dv. So as you can see, I have converted everything into volume. The right hand side will be the integration of x cross the mu double dot dv. So as you can see, we have wrote the two equations but using only integral volume integrals, right? So this is gonna make it more convenient, more practical, more easy to be solved if we already mathematically talk, right? Now we're gonna do even more simplifications over these two equations. We're gonna do more simplifications over these two equations. But before we do it, let us discuss here this t that we introduced. So as we mentioned, to be able to apply the divergence theorem, we have to convert this big T, this uppercase T, into n dot T lowercase. T lowercase, it should be tensor. As we discussed, this T, it should be tensor. But this one is a vector, right? And in itself, it is a vector. So what is this tensor? This tensor is commonly known as the stress tensor. This is the stress tensor that we basically use and we're gonna use through this course. This is how we introduce the stress tensor. This is the origin of the stress tensor. Okay, so the stress tensor, it is related to the surface tractions acting on the continuum through this relation, equation 14. So if I ask you, for example, what is the relation between the surface stress, the stress tensor of a continuum to the surface forces acting on the continuum, this is the direct relation. Because why? the T, it is surface force that act over the surface. And we knew from the mechanics of material that a force over area gives stress. We knew this thing from the continuum mechanics, right? So if this force is T, which is the surface force, and you divide over the area over the surface, this is gonna give us the stress but over the surface. The stress over the surface. But basically, it is hard for us to deal with the stress over the surface. Even it is hard for us to measure this stress experimentally. It is easy for us to measure or find the stresses related over the particle located in the core. So that's why we had to use the divergence theorem to convert the surface integral into volume integral, right? So if we converted this force into, or simply we can relate this surface force into the stress inside the core, which is this T. Make sense? In the continuum mechanics, we used to give it a name as sigma. And I'm gonna let you know how we drive the sigma now. But for now, let us use the general expression of the stress over the stress as T. So again, T is just the stress that it is commonly, this is the stress that is commonly used in the continuum mechanics class or even the machine design course. This is the conventional stress tensor, but it has a little bit of changes, but this is just a stress. So simply this equation 14 relates these forces acting over the surface directly to the stresses that should be generated in the continuum because of this external force T. Make sense? So I will return back again to this equation to explain or to write this equation explicitly in the x direction, y direction, and z direction. But for now, you should understand the equation 14 relates the stresses generated inside the continuum to the surface traction acting on the continuum. And we're gonna explain in detail what does it mean stress after a few minutes, right? But for now, let us return back again to these two equations. Can we do more simplification to these two equations? Yes, we can. For example, if I ask you to combine all of this integral, all of these just integrals, right? So instead of splitting them over multiple terms, is it fine if I combine them, all of them together into one just integral, volume integral? Yes, we can. The same thing for the second equation. So let us do it. So if I can rewrite again these two equations, the first equation, what I'm gonna do, I'm gonna collect F plus nabla dot T negative. I'm just gonna move this one to the left hand side, negative mu double dot, and I'm gonna do the integration to the all equals 0. So we're gonna end up the integral of V of F plus nabla dot T, and remember T again, this is the stress tensor, and plus the, or negative, it should be negative, the mu double dot, because I moved this one to the left side. All of this should be integration over the volume, it should be 0. So this first equation, it should be the same. This is like 1 dash. It should be the same equation like this one. Make sense? I just collected all the terms in one integral. Do the same for all of these terms except this term. Just leave this term separate, for example, to make it easy. So I'm going to collect x cross f plus x cross nabla dot t negative. I'm going to move this one to the left side. So I'm going to have the integral of x cross, even the x, I'm gonna consider the x as a common factor. If you moved all of these, this one to the left side and collected all of these three terms together, you can have the x as a common factor, right? So we're gonna have like x cross the f plus nabla dot t negative mu double dot dv. So this is the sum of these three terms. Negative this term, which is gonna be the negative of the integration over the volume of the epsilon double dot t dv equals 0, and this is gonna give us the second equation. Still the same equation, but I just combine some volume integrals, right? All right, so there is something that I'd like to mention about these two equations before we move further. For this first equation, is to state that the integral, the volume integral of all of these force terms, because all of these just forces, mu double dot, it is inertial force, if this is the body force, if you remember, nabla dot T, this was the surface force, right? This is the thing that we obtained this term because of the surface structure, right? So anyway, it is a force. So it means that all of these fields are different forces that should be acting over a continuum. And their integration over the volume equals 0. So the question is, if the integration of all of these forces over the volume equals 0, does this mean that these forces, their sum equals 0? So for example, is it fine if I say that F plus nabla dot T negative mu double dot equals 0? Since the integral is already 0, does this mean that this equation equals 0? Does this mean that this equation is correct? No, it doesn't mean that this equation is correct, mathematically speaking. A very good example to this case, but this equation is going to be correct according to the classical mechanics, as I'm going to let you know. But mathematically speaking, it is not conditional. What does it mean? It means that if the integral over the volume or the integral function equals 0, this doesn't mean that what inside the integral itself, it should be 0. It would be 0 or it would be any other function. A very good example, if I ask you what is the integration of the, for example, if the integration of cosine x dx equals 0, does this mean that cosine x equals 0? No. Why? What is the integration of the cosine? Give sine. Okay, give sine x equals 0. It means that if you just solve the equation, this is going to give us 0. Solving for x, so x it should be 0, it should be pi, 2 pi, and so on, right? Then if you substitute for this x, so this should be the value for x. X cosine 0 gives 1, cosine pi gives negative 1, and so on. So what does it mean? It means that the cosine itself, it is not equal to 0. While the integral itself equal to 0, this doesn't mean what is inside the integral, it should be 0. This is mathematically speaking, right? So just leave this one on the side here. So going back here to this point, this means that if this integral equals 0, this doesn't mean necessarily that this term it should be 0. But one of the characteristics of the classical mechanics that we're already using, that even this term, it will be 0. In some other function, here I give you an example of the continuous function like cosine x. If we are using some other function, probably the integral will be 0 due to because that what is inside the integral is already 0. You got my point? It means that there should be something 0 here, right? So that's why the integral of 0 gives 0. And this is the case of the classical mechanics. In the classical mechanics, the equilibrium or the sum of these three forces, all of them together, is equal to 0. That's why their integral over the volume is already 0. Make sense? This is one of the characteristics of the classical mechanics theory. But there are some other theories like the non-local mechanics, more advanced theories, that this integral, what is inside, or this integral, it will not be equal 0. So what is inside, it is not necessary to be 0. It means that it's going to be different things. But one of the characteristics of the classical mechanics, that whereas the integral over the volume is 0, also what is inside the integral itself, it is 0. So what does it mean? It means that it's fine to remove the integral for this equation. The same thing applies for the second equation. That is fine to remove the integral. Okay? Because anyway, this term, what is inside the integral, what is inside the integrals are zeros. So if we remove the integrals, it means that here we're already collecting summing all the forces acting over the continuum because of the integration. But if we remove the integral, we are getting the force acting over one single particle. It should be also 0. This is according to the classical mechanics. Make sense? For any other theory, that the equilibrium over one single particle, it is not necessary to be 0. Like the non-local mechanics, probably at the end of the class, I can give you introduction about this non-local mechanics. But for now, for the classical mechanics, that any particle, it will be equilibrium by itself with the surrounding particle locally. At its position, it is already in equilibrium Also globally over the overall continuum, it is also in equilibrium. Like, what does it mean this? It means that the integral of these fields over the volume is zero. Also their sum without the integral is also zero. So if we decided to remove the integral, and this is gonna make it more simple, here we would like to write a practical form of the equilibrium equation of the continuum. Now we can get rid of the volume totally. So we're gonna end up with the first equation will be simply f plus nabla dot t negative mu double dot equals 0. This is the first equation. We're gonna give it like one double dash. And the second equation is, in this case, the second equation will be the x cross the f plus nabla. Okay, wait. It will be nabla dot t negative mu double dot negative the epsilon tensor double dot t equals x, equals 0. This is the second equation, 2 double dash. This is just, I get rid of the volume integrals. Make sense? So according to the first equation, this term, it should be 0, right? So what does it mean? It means that this term as well, it will be 0. So this term will be cancelled. So the first equation, we're just gonna carry on the first equation, which is gonna be f plus nabla dot t negative mu double dot equals 0. This is the first equation. And the second equation will be simply negative epsilon double dot t equals 0. And this is going to give us the second equation. These two equations simply are the simplest form of the equilibrium equation, or a very simple form of the equilibrium equation or the equation of motion of a continuum. These are the equations of motion of a continuum, according to the continuum mechanics. Make sense? So we did very simplification. We end up with very two simple equations. Like this is again, what is this F? This is the body force. What is this T? This is the stress tensor that we're gonna discuss more about it today. Also, in the classical in the continuum mechanics class, this is the stress tensor, the conventional stress tensor that we used before. What is mu double dot? This is the inertial force, which is mass times the acceleration. This is simply the equation of motion of the Newton law. This is the equation of motion according to Newton's law, right? But this is for a continuum that can deform because of this stress tensor field. For example, in the dynamic class, this term nabla dot t, it was excluded from the equation of motion. So that's why, for example, in the dynamic class, we said that the force, it should equal to the mass times u double dot, which is the mass times the acceleration. This is in the dynamics. Because in the dynamic class, you studied rigid body motion. What does it mean, rigid body motion? The object was rigid. There was no deformation. But here we're going to consider the object that it would move or deform, both. So that's why this term has been included, nabla dot t has been included to account for the possible deformation of the particle because, or the continuum, because of the external force. Make sense? How about this second equation? This second equation, we got this one because of the moment. If you remember, the origin of behind this equation is the moment equation. That this is the simplified form of the moment equation. This is what we're gonna get at the end. Make sense? So simply after we do all of these calculations, I did here the integration. These are the equations again. We end up with these two equations here. Make sense? So where epsilon again, this is the permutation tensor. Where epsilon, it is epsilon I j k delta I delta j delta k. Now, I'm gonna discuss something here regarding this m. What is m here into this equation so far? This m, according to what we defined starting from the discrete system of particles, this m, it should be the mass of the particle, right? This should be this m, it should be the mass of the particle. But as you can see, we has been moved totally from talking about the particle to the continuum. As we discovered that the number of particles inside the container are huge, are so many. And if we're going to talk about polycrystalline material, for example, this particle would be the grain. So for example, in the classic and in the mechanics of material class, the instructor or the faculty, he didn't ask you about the mass of the grain inside the material, right? Or the mass of the particle. Like in basically or practically speaking, since we had been moved to the continuum, it is not convenient anymore to use the mass of the particle. We have to replace the mass of the particle to something that is related to the continuum that we're already talking about. Make sense? So, what is the mass of the particle? The mass of the particle can be related to the density or the mass of the continuum. You can consider that this is the mass of the continuum. The mass of the continuum divided by unit volume. Why? Because, for example, you do have a volume that is consistent of very small masses. Each one of the and the number of these very small masses is huge, is infinity, right? So if I ask you, or simply we can write this equation. If I ask you what should be, you do have a continuum like this one. And this continuum includes so many particles, and each one of these particles is m, has a mass m. So what should be the mass of the overall continuum? It should be the integration, or we can say that the sum of the masses, right, of the mass of the particle. But since we're already dealing with continuum mechanics, we cannot sum anymore. So this mass, it should be the integration of the mass over the volume, right? This is gonna give us the total mass of the continuum. So this should be the mass of continuum. But this small mass, it should be the mass of the particle. Make sense? So if this mass of the particle is constant everywhere, it means that it has homogeneity, and this is according to the classical mechanics, right? Like we're assuming that this is a homogeneous material, so we can have this m outside the integration. We can move this m outside the integration as follows. So we're gonna end up that m uppercase is gonna be m times the integration of dv. This integral gonna give us just v, the volume. So this is gonna give us the mass times the volume. Make sense? So that is fine to say that the mass of the particle, the mass of just one particle is gonna be the total mass of the continuum divided by the volume of the continuum. Make sense? And from physics, mass divided by volume, this gives us density, right? This is from physics. So what does it mean? It means that the mass of the particle, it is equivalent to the density of the continuum. This is the mass density. This is the mass density of the continuum. Make sense? So simply we can get rid or remove or replace this m with rho. What is rho? This is the mass density of the continuum. Because if you have a continuum that is consisted of so many particles, and we have no clue how much is the size or the mass of one particle inside the continuum, but we can find the density by weighing, find the weight of the particle, of the continuum of the material. You can simply, and divide by the volume, you can simply end up with the density, right? So simply we can calculate experimentally, we can find the density of any material by weighing the material, which is very easy. So simply you're gonna replace, it is convenient since we already moved to the continuum mechanics to replace m, which is the mass of the particle, with the density, which it should be the density of the continuum as already given here. Make sense? So this is, I can simply remove this one and just replace this one with the rho, and this is what we're gonna do next. It means that from now on, we're gonna replace this m with the density. Make sense? Now what we would do is to discuss more these two equations and discuss the stress in relation to the surface tractions. Okay, so let us cover these two equations again. The first one is first one is nabla dot T plus F, the body force, equals, we can move the mu double dot to the right side as we just reset back again, like as we already moved this one to the right hand side. So we're gonna have the nabla dot t, this is the stress tensor, and this is the divergence. This is the divergence of the tensor plus the body force equal the mu double dot. And the second equation is the negative of epsilon double dot t, which is the stress tensor, it should be 0, right? So this is the first equation, and this is the second equation of the dynamic equilibrium of the continuum. All right, so now let us talk about this second equation. This is negative epsilon, and epsilon, as we mentioned, this is the permutation tensor, double dot t. So let us work over this tensor a little bit. So this epsilon, it should equal to epsilon I j k delta I delta j delta k, as we mentioned above, right? So this is the epsilon term, negative, and we should have double dot here to the t, since we already used I j k, so the t will be t m n, for example, delta m delta n, any two other indices. It should equal to 0, right? Then just collect the terms and do the operation, the dot product, the double product, the double dot product over the unit vector. So we're gonna end up with negative epsilon I j k t m n, right? And this is gonna give us delta I. Then we're gonna have the dot product. It will be distributed between the delta j, delta k, delta m n. So I'm gonna make it like 1. I'm gonna write one step here, double dot of delta m delta n equals 0. Then this is gonna give us negative epsilon I j k, the delta m n delta I, and this will be, you're gonna do the dot product of this 2 times this 2. So this is gonna give us at the end delta k m delta j n, it should be 0. Make sense? Then if we did here, okay, let us do one more step here. So to get rid of this delta and delta ij, this means that delta km, it means that k and m, it should be the same index. Use the same index for k and m and the same index for j and n. So we're gonna end up with negative epsilon ijk and ijk, and this m, it will be k, and n, it will be j, right? Delta I equals 0. So what is this term here? To get rid of the epsilon, this is gonna give us like negative, because this is gonna give us vector at the end. We just end up with delta I. This means that we just have one vector, right? So negative, this epsilon, it will be, to get rid of the epsilon, we're gonna write the delta kj negative t, the t kj negative t j k delta I equals 0, right? So this is the equivalent form of the second equation. As you can see here, if I ask you to multiply this equation times 1 over 2, if I multiply it here times 1 over 2, do you think that I did change this equation? No, since the right hand side it should be 0. Like you're gonna multiply 1 over 2 here times 1 over 2 on the other side. So it means that anyway the right hand side is still 0, right? And if you remember from the tensor analysis or the tensor calculus that we discussed, this term, which is 1 over 2 tkj negative tjk, this gives a skew symmetric tensor. This gives a skew symmetric tensor. If you remember from the tensor calculus that the skew symmetric tensor, it has 0 diagonal component, and the off diagonal component, they should be identical but of 2 different signs. So, and if in case that you'd have a general tensor, that has 9 independent components, to find the skew symmetric part of this tensor, the skew symmetric part, it should be 1 over 2, the tensor negative, its transpose. You got the tensor negative, its transpose. If we multiply this half here, so this will be negative, this will be positive, it's gonna be the same. It means that here we are talking about a skew symmetric tensor, right? And this part here into this equation, okay, and this part into this equation, this indicates that this part is the skew symmetric, this is the skew symmetric part, the skew symmetric metric part of the tensor T. This is the skew symmetric part of the tensor T. So this should be the second equation, this should be the second equation, right? But in the expanded form. So according to the second equation, we're going to conclude that the skew symmetric tensor, it should be 0. Very simple. The skew symmetric tensor, or this, not the skew symmetric, the skew symmetric part of the general tensor T, it should be 0 according to the second equation. So this is still the same form. This is the same second equation, but the x in terms of its component, right? I just rewrote this equation in terms of its component here. So according to this equation, this indicates that the skew symmetric part of this general tensor T, it should be 0 according to the second equation. And you should understand that in this equation, T is a general tensor. What does it mean, general tensor? As we mentioned, a general tensor is the tensor that has 9 independent components. It has 9 components. And a general tensor, as we discussed in the tensor calculus, it can be decomposed into symmetric and skew symmetric parts. This is the skew symmetric part of the tensor. Or to be more accurate, 1 over 2 times epsilon double dot T, this gives the skew symmetric part of the tensor T, which should be 0 according to the second equation of the dynamic equilibrium of the continuum, it should be 0, right? So if I ask you to decompose this T into symmetric and skew symmetric parts, so we're gonna say that I can write this T as sigma plus sigma with a hat. This sigma is the symmetric tensor. This is the symmetric part of T tensor, but this sigma with a hat, assume that this is the skew symmetric part of T tensor. Make sense? And you should understand, as we define, that this symmetric part, it should be 1 over 2 T plus its transpose, while the skew symmetric part, it should be 1 over 2 T negative its transpose, right? And in terms, these are tensors. In terms of component, it means that the skew symmetric part is this one. So according to the second equation, or in other words, if I ask you to substitute with this T as sigma plus sigma hat, just substitute this equation into these two equations. So we're gonna end up with here. We're gonna end up with the first equation will be nabla dot, right? T, it will be sigma plus sigma with a hat, the symmetric and the skew symmetric parts, plus the body force equals mu double dot, and we agreed that we are going to replace m with the density, right? As we discussed above, we're gonna replace this one with the density, so it will be rho u double dot. This is gonna give us the first equation, and according to the second equation, negative epsilon double dot sigma plus sigma with a hat, it should equal to 0. Or in other words, the second equation, it will be directly the sigma with the hat, it should be 0 according to the second equation as we demonstrated here. Even if you try to multiply this epsilon double dot times sigma, the symmetric part will be eliminated anyway, okay? But we already demonstrated that this second equation gives a skew symmetric part of the tensor that it should be 0. Right? So according to the second equation, this epsilon with a hat, it should be 0. So if you substituted the second equation into the first equation, we're just gonna end up with one equation, that nabla dot sigma plus f equals rho u double dot, and this is the only equation of elasticity that if you open any textbook, you're gonna find this equation of the linear elasticity or even nonlinear elasticity. Like this is for any continuum mechanics. These are the equations of motion for the continuum based on the classical mechanics. If you open any textbook on the continuum mechanics or linear elasticity, you're gonna find the equation of motion represented into this form. But what I've demonstrated here, I showed you how did we drive these equations or these equations of motion starting from the mechanics of a discrete system of particles. Make sense? And that's why, and this is what we're gonna consider through the linear elasticity class, that this sigma is the stress tensor. This is the stress tensor that in the mechanics of material class that you had an experience with this tensor before. All the stresses that you consider in the mechanics of material class were sigma. These sigmas, this is a symmetric tensor. This is symmetric tensor. So this is again the equation of motion that we're going to use for the continuum mechanics that depend on a stress tensor. And one of the characteristics of the stress tensor in the classical mechanics that it is symmetric tensor. But something that you should understand, that generally the stress tensor, it is a general tensor, that it should have 9 independent components. Some of these components, or this non-independent component, this general tensor, it has symmetric part and it has a skew symmetric part. But according to the classical mechanics, the skew symmetric part is 0, so that's why we can just consider that the stress tensor is a symmetric tensor. But originally it should be a general tensor, has symmetric and skew symmetric. But based on the dynamic equilibrium condition that, and especially equation 2 of the continuum mechanics, we end up that the skew symmetric part is 0, and that's why we're already using in the classical mechanics only the symmetric tensor, or the stress tensor in the classical mechanics is symmetric. Why? Because according to the dynamic equilibrium of the second equation, which is related to the moment of the dynamic equilibrium of the continuum, this equation we have demonstrated that this equation demonstrates that the skew symmetric part of the tensor is 0. So that's why the stress tensor, it should be symmetric. Make sense? So this is for the equations, and this is the main equations of motion that we're gonna use through this course for the continuum mechanics. Okay? So what I've did here, I started from the mechanics of particle. I did formulation till we end up with this equation that we're gonna use. Now what we would like to discuss here into this equation, that this sigma is the stress tensor that we are going to discuss, and the equation of motion, it has nabla dot sigma, and F, it should be the body force, U, this should be the displacement field, where rho U double dot, this is like the inertia force but per unit volume. So you should understand that this body force, let me just write an expression, the meaning of all of these terms. If this is the body force, this is the body force per unit volume of the continuum, because we eliminated, we removed the volume, right? And what is this body force? We said that it would be interaction between the particle, it would be external force, it would be the weight of the particle, pressure, whatever it is, right? Also, in addition to this one, we do have sigma, which is the symmetric stress tensor, and nabla dot v, nabla dot sigma, this is the divergence of sigma, this gives force vector, but this is force per unit, this is force per unit volume as well. The rho U double dot, this is the inertia force of the continuum per unit volume, as well. So all of these quantities that were already represented in this equation, all of them are forces per unit volume. Make sense? If we decided to write this equation, so this sigma is a tensor, this F is a vector, this U is a vector, but nabla dot sigma gives a vector as well. If we decided to write this equation in the explicit form, in the x direction or y direction or z direction, since these are vectors, any one of these vectors has 3 components, right? So it means that we should have ux, one equation for ux, one equation for uy, one equation for uz. So we're going to end up with 3 equations. So let us write these 3 equations first. So if we decided to write these 3 equations here, the first one, It is nabla. Let us just work over nabla. So nabla, it will be the partial by partial xi delta I dot sigma, which it should be like sigma jk. You have to use two different indices, dj delta j delta k, right? Plus the body force. I has moved to another term, right? I moved. This is one term. Now I move to another term, which is Fi delta I. I'm going to use the same indices that I used them before. Starting from I, since I already started with I, so I have to start here with I. But this is the only vector that I have in the second term equals, this is the F term, here rho u double dot. So it's going to be the rho ui double dot, right? Delta I, because ui is just a vector. Then do the multiplication here, or the operation over the unit vector. So this is going to give us the partial sigma jk by partial xi. Then we're going to have delta I dot delta j and then delta k plus the fi delta I equals rho ui double dot delta I. Make sense? Then what we're going to do, we're going to end up here. That is fine to write this sigma jk. We can write this sigma jk as sigma jk comma I. And here this is going to give us delta ij. So what does it mean? You should use the same index for both I and j. So let us use I for both of them. So we're going to end up with sigma j, it will be I, k, partial by partial sigma by partial xi. That is fine to write this one as comma I, as we discussed before in the tensor calculus, right? Delta, this is going to give us just delta k here, plus fi delta I equals rho ui double dot delta I. So as you can see, this term, it is a vector, but the vector we are using for the vector, the index k, here it is a vector, but we are using for the index as I. Here we are referring to the vector as I. So make these three terms consistent. So what does it mean? It means just replace this j with I, or this k with I. So if I decided to replace this k with I, so I have to replace I with j, for example. Like for example here, we said that delta u with the same index for I and j, you can use j for both of them. So I can use here j and replace this one as I. So I can write this equation one more time in another form. This equation, I can write this equation as sigma ji comma j. I just replaced k with I and j with j, I with j, because I didn't use any j's here. Delta I plus fi delta I equals rho ui double dot delta I. So I do have consistent vectors for the I. That is fine even to get rid of this delta I with this delta I with delta I, to end up with just the equation as sigma ji comma j plus fi equals rho ui double dot, and this is gonna be the equation of motion, but in terms of the terms, or in the form that depend on the terms of all of these vectors. The first vector, which is the body force, this is the stress tensor, but this is the gradient of the stress tensor, and this is the u, which is the displacement vector. If we decided to write this equation in the explicit form, in the x direction and y direction and so on, remember that the main vector that we're already discussing here is I, but the j is a dummy index. Like this is the main index and j is a dummy index. So for I equals x, it means that you're just gonna fix I is x. So this is gonna give us sigma jx. This is gonna give us sigma jx comma j plus fx equals rho ux double dot. Then j, as you can see, there is repeated index over the same term. It means that it is dummy index, so I have to repeat over the j. One time that j equals x, one time that is y, one time that is z, and sum all of them together. So explicitly it will be like sigma x comma x. Now j is just x, plus sigma. Now I'm gonna use j as y, so it will be y x comma y. Now j as z, so it will be sigma zx comma z plus fx which is the body force, equals rho ux double dot. And this is gonna give us the first equation, the first of the three, in case that I equals x. How about if I equals y? We're gonna do the same. So simply I, it will be y. So all these i's will be y. So this is gonna give us sigma j y comma j plus fy equals rho uy double dot. Now j is a dummy index again. So what does it mean? It means that I can write this as xy comma x plus 1 time that j is y, so it will be yy comma y, and sigma zy comma z, right? It should be comma z plus the fy equals rho uy double dot, and this is gonna give us the second equation. If we did this is for I equals y, do the same for I equals z, automatically it will be sigma xz comma x plus sigma y z comma y plus sigma z comma z plus fz equals rho u z double dot, and this is gonna give us the third equation. So these are the three equations, the explicit form of the compact form of the equation of motion. This is the equation of motion in the compact form. This is the explicit form of the same equation. As you can see here, the equation of motion of the continuum, it is three equations. The equation of motion are three equations. So what does it mean? This fits with the concept of the classical mechanics. The concept of the classical mechanics state that the continuum, it is a composition of particles, and each one of these particles is a point. As we discussed before, a point, it has three types of degrees of freedom, that it can move along x with ux. So ux, this is the displacement of the particle along x. uy, this is the displacement of the particle along y. uz, this is the displacement of the particle along z. So that's why we end up with just three equations of motion to describe the 3 degrees of freedom of the particle that belong to the continuum. Make sense? So it is, everything is related. The mechanics of particle is related to the mechanics of the continuum. And again, in the classical mechanics, we assume the particle as a point. A point, it has only one type of degree of freedom, that it can only move along x, y, and z. So that's why the equation of motion in the classical mechanics, it is only 3 equations. But for some reason, and this is what basically considered in the advanced theories of mechanics, for some reason, if the particle is a volume element that can move and rotate and deform, so there are some extra degrees of freedom. So the equations of motion will not be just 3 equations, will be definitely more than 3 equations to account for the extra degrees of freedom. All the time, the number of degrees of freedom of the particle equal the number of the equation of motion of the continuum. Since we do have the particle as a point, it has only 3 displacements, so that's why we end up with 3 equations of motion that describe the continuum equilibrium. Okay? So, what we did here is we did a general formulation starting from the mechanics of particle till we end up with the equation of motion of the continuum, and we wrote these equations of motion in the explicit form in the 3 equations as already given here. Make sense? So this is for this part, which is chapter 1, or the first part of the class, is just to understand, the objective is to understand the mechanics of particle and how it is related to the continuum mechanics, how we can drive the equation, these equations. These are the equations of motion that we're going to use them a lot through the whole course. These are your main 3 equations of motion that we're going to use through this course. So what I've did here, I did intensive discussion on the formulation of these 3 equations starting from the mechanics of particle. Also, we have discussed how these mechanics of the continuum are related to the mechanics of the particle. Okay, and this is the end of the first part, or chapter 1 of this course, right? So thank you, and see you in the next video. In the next video, we're gonna discuss the stress. We're gonna discuss this stress component, or the kinematical variable. In terms, we're gonna go deeply through the continuum mechanics and especially linear elasticity, and we're gonna discuss the stress component and the displacement field and the deformation field, what they mean. And we're gonna form also the stress-strain relation, the constitutive, which are commonly known as the constitutive relations. So, and in the next video, we're gonna discuss something that you should have a little bit experience about through the mechanics of material class. So it should be much more simple than this one. I know that this one, it would be a little bit challenging but as I mentioned, it is important to understand these concepts starting from the mechanics of the particle. All right, so thank you for now and see you in the next video.